right, so thanks everyone for being here despite the good weather. And I know that I'm the last guy of the day, and I'm standing between you and dinner. Luckily enough, dinner will be served at 7:30, so we have just about 2 hours for this talk. I'm just kidding, it's just gonna go. So I tend to overrun, however, so luckily enough, please, if the science doesn't work, just do something physical, don't be too harsh. So what I'm gonna be talking to you about is a bit about mobile security and something that I've started to be doing, and we started to be doing at Royal Holloway a little while ago, to try to understand this new slew of threat. I mean, is it a new threat? Is it something that we can deal with? Is it something novel? What are we dealing with? And so I'm trying to understand, I hope you guys, the takeaway points is actually try to understand how to deal with this problem. So a bit of introduction by myself. So I'm originally from Italy, so I studied at University of Milan, and then during my PhD, I just went abroad, because Italy is messed up, it's still messed up, it was messed up back then. So I had the chance to work with really good people, so all the praise to them, and all the shame to me for all the mistakes I can make today. So I spent quite a bit some time at Stony Brook University, then I got a postdoc position offered at UC Santa Barbara, and I stayed there roughly 2 years, a bit less than 2 years. Then I moved at Vrije University in Amsterdam as a postdoc again. I spent 2 years there, and I've always been working in system security and malware analysis and detection. So this is sort of my expertise, what I'm trying to do basically, at different levels. Okay, and since January 2012. I joined, so actually I came here to the UK. I'm currently a senior lecturer in the information security group at Royal Holloway, University of London. So I know that I was told that I should have just one slide for, introducing myself, and this is just one slide. The next thing is more like an icebreaker, right? Talk about Royal Holloway. This is not Royal Holloway. Now, for those of you who are not from the UK, this is Windsor Castle. And of course, I don't live here, it's not my residence, it's very bit pricey. So this, on the other hand, is Royal Holloway, this is the founder's building, so it's a pretty Victorian style building. My office is not here, of course, I'm a computer scientist, so you have crappy office in crappy building going over there. It's all right, you're focused on doing research, right? And this is not Royal Holloway, this is Hogwarts, right? Because people said, Royal Holloway, resembles Hogwarts. I don't know whether this is true, but I was told this, and I just wanted to have a slide. That's it. So let's talk about Android now. Why Android? Okay, these stats are a bit dated. So I believe September 2013. So numbers have actually grown since then. But with more than 1 billion Android-activated devices, it is sure nowadays that mobile platforms have become ubiquitous, right? Everyone has a mobile platform, right? Tablet or mobile phone. Mobile marketplaces actually drive the entire ecosystem of the mobile environment. We have, I believe, at that time in September 2013, something like more than 1 million installed applications. I mean, now numbers have grown, and more than $9 billion of US dollars in revenues. And those applications are very easy to use, very nice user interface. You use it for pretty much everything. So they just substitute surrogates for traditional computing environment. So you do banking transactions, you store your sensitive information there. We just got very nice talk in the morning about people who said data stored locally, shouldn't be stored locally, but it is stored locally, and all sort of ways that you can use the devices, pretty much for everything, right? And of course, it's a very wealthy ecosystem, so it's very easy to get your app out there. So a few talks before, I remember that there were a few comparisons between iOS and Android marketplaces, so iOS App Store and Google Play. I'm not going to go into the differences of whether it's easier to get onto Android marketplace. Well, it is. But basically, so it's very easy. So that's why people just write an application and then they just hope for the best. Maybe they can make a few quid out of it, right? And it's good. So everyone can do it. It's just very different business model. Very big numbers of revenue. And of course, the bad guys are just going after this. I'm still in line right here. Yes, I shouldn't go over there, otherwise for a camera. So this is also what attracted the bad guys. And because numbers do not look so scary yet. Because if you look at traditional malware, traditional viruses, or whatever, call it malwares, generic terms, I believe vendors nowadays have something like 130 million, 150 million unique samples in their databases. Now, if you look at these numbers, or way, 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 way below. So this is a figure that comes from Trend Labs. It's a pretty recent figure. Things change. I mean, numbers change from vendors to vendors, but the order of magnitude is still the same. So we're around 2.1 million, 2.5 million of unique Android malware samples in the databases overall. So not staggering numbers, but they're growing very fast. And it's probably the time to start thinking doing things right, instead, probably learn from our past. So we've been stuck with signature-based detection for a while, and then suddenly we realized, well, no, we cannot deal with that anymore. And of course, the AV industry is doing a lot more than just signature-based detection. But maybe we can do something proactively now that we have this low number on mobile devices as well. In terms of what kind of threat this malware poses, well, the ranks varies depending on the period where you look at the trends, but mostly basically you have adwares, so massive adwares that are pushed on your devices. You have premium service abusers, so premium SMS or premium calls, although recent versions of Android are trying to mitigate that issue by blocking those. Information can be stolen. And then you have applications that are just fake applications, pretend to be other applications, then download other applications. And you have, of course, other applications that try to exploit the system, Android system itself. It's just a broad categories of things that are happening there. So before getting into a bit more detail of what we're trying to do, let's talk a bit about Android. I mean, this has been touched already many times today, so I'll go very quickly. And that's why I just titled the slides, the not so short introduction to Android. For you guys that are fan with LaTeX, I'm sure, I hope you guys have picked that up, because I really spend a lot of time for that. No, I'm just kidding. So Android is just a modified Linux kernel. So if you're familiar with Linux, it's good. So there's a little bit more than that, of course. And Android applications are sandbox, so they run in their own address space. And they run on top of Dalvik VMs, so on top of a Java-like virtual machine, okay? Of course, as in Java, you have also Java native interface. So although you write code in Java mostly, you can write code in C++ and access the JNI interface and execute native code. So already here, we sort of have, when you think about doing analysis of this app, you sort of have to think about what you're going to be looking at. You're going to be looking at binary code, native code, or you're going to be looking at Java-like bytecode, or a combination of the two. Well, it depends on what you have to do, and there are pros and cons in doing both. And there are different techniques to doing that. But let's just keep it that for a point. The applications also are logically divided in different components. You have activities, services, broadcast receivers, and I forgot, content providers. So activities, think just about anything that is a graphical user interface associated, that is an activity. A service, if you're familiar with the Unix environment with Linux, it's a daemon. Just think about a process that runs on the background and provides a service, like the name suggests. For instance, if you want to send an SMS, then you have to contact the ISMS service to send out the SMS. There is permission checks that's going on, but it's basically what happens. So I'm just trying to simplify things. Of course, there are a lot of details. Broadcast receivers, instead, they basically react upon the receipt of a particular message. For instance, when the boot is completed, when an SMS is received. And of course, you have to tell the system that you want to interact with this event, for instance, and we'll see how you tell the system, but it's been shown also today. Remember Andrew, when he had spoken about intent. He has shown a lot of examples of how you can declare these things. And then you have content provider that we're not going to be talking about this in the talk, but they're basically storage agnostic, access control, ACL control abstraction to access data. So it's just a repository that you have APIs and permissions that you can store your data there. So the security model is actually quite interesting because, in a way, the design tried to enforce what is known as a principle of least authority. So by default, application shouldn't be able to do anything, any harm to any other application or to itself, themselves in a way. That's why, well, again, we have sandboxing. Every app has its own user ID and group ID. Of course, this is the simplification. You can have application with the same user ID, but simplicity just assumes that every app runs with their own user ID, so if it comes from different developers, for instance. And you have system-wide discretionary access control enforced. in some cases. So if you want to access a file, that's the classic Linux discretionary access control checks that are in place. If you want to open a network communication, then you need to request a permission that associate your application with a specific groups that is allowed to create sockets to communicate over the network. On the other hand, for more Android-specific action, you need to request permissions. And permissions are enforced throughout the system. Some permissions are enforced, of course, in the address space of the application that requests the permission, but it's not too safe, of course, and this is replicated, of course, the check in the stub of the service that carries out the permission for yourself. But of course, permission must be requested up front, and you need to agree to the permission, the most dangerous one. You need to agree before the application is installed. And because any application that runs on the system is subjected to the same permission model, to the same security model, regardless of whether it's something that starts in Java or goes natively. Intents, we've seen intents this morning, and they're basically abstract representation of an operation to be performed. It's an action, so you want to do something, you want to send an SMS, you represent that action as an intent that you send to a service, for instance. You can send intent also through your application. Remember, takeaway for this morning, always be explicit when you send intent, never be implicit. If you haven't followed Andrew's talk, we can talk offline, but there are reasons always to be explicit and always say to whomever you're sending the intent to. But it's basically what it creates, the possibility to do inter-process communication, because the whole system relies heavily on inter-process communication and remote procedure call invocation. Because you have these applications that are, just imagine this application that are sandboxed, and if you don't have a method to communicate with the rest of the application or with the system, then you're just confined to your own environment. So IPC is very important in the system, and we'll see it actually plays a critical role in the analysis that we want to do. So another thing that comes with Android applications, the manifest files that just describe some resources that the app might use. And for instance, you can use the Android manifest to declare the permission that the application requests. In this case, you have a fictional application that requests permission to receive SMS, send SMS, and access the internet. And here below, you can see, for instance, that an application is registering itself to the system to react to SMS received event. And in this particular case, there is a class that is called SMS receiver that will be instantiated by the system, and a specific method will be invoked that basically it's the method that will be delivered the message, the incoming message. And this delivery will come through an intent. So we have said that basically IPC and RPC is very important in the process communication. Remote procedure call invocation is very important. How does it look like? From a perspective of the user space application. From a perspective of a user space application, it's very simple. So this mechanism is implemented in kernel, but instead of relying on the classic IPC mechanism that Linux uses, Google has decided to implement Open Binders as a specific version of as a fast and efficient IPC mechanism, IPC and remote procedure call mechanism. That's called Open Binder, and the specific implementation is called Binder. So the way that it looks is like a virtual device, dev binder, where applications just open the device. They want to perform this inter-process communication. They open the device and they issue IOCTL calls. So system call. It's just a system call. And this is also another key point, okay? And then, of course, we're interested in just capturing a few of these messages. Now, this is, not sure about the color. Yeah, I'm sorry about the color. So they look slightly better on my monitor. So to be honest, they don't look too good on my monitor as well. But basically, so there was just an attempt to outline a bit of research that's going on malware, Android malware analysis. It's a very hot topic, so everyone is doing it. When industry is doing it, and the academic environment, academia is doing a lot of research in that. And you have all sort of different approaches that have been proposed so far. Some of them are just focusing on static analysis, others are just focusing on dynamic analysis, others are just a hybrid of the two. Some people are just doing, they rewrite the APK to enforce policies in specific points where you can get pop-ups, for instance, whenever something is happening, something fishy is happening. So I'm going to be focusing on a bit more on dynamic analysis, because this is what we're doing, with all the limitation of dynamic analysis, of course. And those are the challenges we'll be focusing on in the future, and I will highlight on those. But basically, if you look at static analysis, well, the advantage of using static analysis is that potentially you can see the whole behavior, because you analyze statically, the whole application doesn't depend on any input. The problem is that application can be obfuscated, and it might be hard. So now malware, specifically malware, they're starting to add sort of a bit of anti-static analysis trick. So it becomes a bit harder to follow always statically whatever is happening in the application. Also, if you have dynamic code, then it's a problem because it's dynamic code, so you don't see it in the application. And if you start executing native code, well, you go back to the problems that we've always been having with dynamic code, with static analysis of binaries. So it can be very, very tricky. And on the other hand, on Java, you also have reflections. There's a way to inspect at runtimes objects and call and build methods invocation at runtime. So that's another thing that statically, it's quite tricky to get it right all the time. But there are pros for static analysis, of course. On the other hand, for dynamic analysis, well, you basically is the dual aspect of static analysis. So you don't see the whole application. So whatever you see is just a slice of the execution that depends on the input that you provide. And this is quite challenging because Android applications have many different entry points. It's not just the main activity like classic applications have. For instance, another entry point is when an application registers itself for a broadcast receiver event. That is another entry point. Sorry, just missed that. I was just wondering. No, I'm just kidding. No, I'm just kidding. I'm a shy guy. No. So whatever happened is that, so for dynamic analysis, on the other hand, that it depends on what you want to do and where do you want to run your analysis. So you want either to run it on the device, or again, like many people are doing, practitioners and other researchers are doing, just building dynamic analysis systems to perform large-scale analysis of malicious software. Now, the way that you do this usually is that you set up an emulator or a hypervisor, and you have to do virtual machine introspection to reconstruct the operating system semantics to understand whatever is happening dynamically, like collect, for instance, function calls eventually or system calls. Now, with Android, whatever people have proposed so far is slightly a bit different, because if you look at this from an emulator point of view, you have a first layer of virtual machine introspection that allows you to understand from the emulator the operating system semantics, abstractions, processes that are running, because from within the emulator you don't understand, you don't have the concept of processes. But then also remember the application runs within a virtual machine, the Dalvik virtual machine. So you have to perform another layer of virtual machine introspection to understand the Android or Java or Dalvik VM specific semantics, okay? So doing a two-layer virtual machine introspection is quite complicated because you have to keep in sync all the actions that are happening there and the actions that are happening still at the layer of the operating system or still when you have native code that is invoked. And at the same time, we have many, many versions of Android that are keep on getting out frequently. And chances are that the internal representation of, so while the operating system interface might stay stable, it's very unlikely that it changes very much. The internal representation of the Dalvik VM changes quite frequently. In fact, for instance, nowadays, Google have announced a new runtime system called ART, which is completely different from the Dalvik VM, okay? So if you do that kind of analysis, it's tricky. So it's more like, you're doing a one-off analysis, and then it's a bit problematic to understand whether you can rely on, build on the result of this analysis to perform large-scale detection. So what we try to ask ourselves is that, on the other hand, the literature is really quite full of research done on characterization of processes by doing dynamic analysis. And the way that you characterize the process usually is by monitoring the system call that a process performs. You have various levels of granularity. You can look at the function calls or methods invocation in Java, or you can look at the system calls, because system call is just the lowest interaction possible that you need to have with the system to carry out things. So to perform actions, you need to do that. Now, what we try to ask ourselves is that, instead of looking at the device really as the system as something completely new, and then just keep on looking after the new Dalvik VM, the new ART system. So can we just step backward for a second and then understand, can we actually do system called trace analysis here or is it something that we cannot do it? So, because that would be quite interesting, because at that point you can collect information and quite, with a low overhead on the device as well. So you can do it within an emulator to perform large-scale analysis, but also you can do it on the device. You collect the information that you need, and then you send the information off for offload analysis. So the point is that it's clear that if I see the system calls, I do see the traditional, whatever I call the operating system, the OS-specific actions, like creating a file, opening a socket, creating a process. Now the question is, what happens if the application sends an SMS, access the contact list, make a phone call, access the location, and so forth and so on? How do these operations are realized? So basically, this is what we try to do with Droid, with this system that we've been developing in the past year. And this is just the very beginning, of course. It's not the end of the story. So we tried to come up with something that says, let's try to see whether we can reconstruct the whole behavior just by looking at system call. So we want to observe operating system semantic, but also Android-specific behaviors just by looking at system calls, without digging into the details of Dalvik VM or ART, for instance, because they keep on changing, and we want something that is more stable that can actually work across different versions. So don't take me wrong here. I'm not saying that doing Dalvik VM introspection is wrong. It depends on what you have to do. So if you want to do large-scale analysis, I believe that you need to have something that works across different versions and without spending a lot of effort to keep on updating the system because a new things is just getting out. If you, on the other hand, want to have, want to spend time because you need to do manual analysis, of course, go for more information, as many information as possible. So those approaches are complementary. So what we've done here is that, we try to characterize the behavior of the whole complex behavior just by looking at system calls. Well, the system is up and running. It's coperdroid.isg.rhul.ac.uk. It's whatever you have online is outdated with whatever we are doing at the moment. So whatever it is online runs, it's an emulator that runs a gingerbread image, so it's quite dated. But we're just finalizing, we redesigned the system, we're finalizing it, and it supports all the versions now. So it works pretty nicely, but it's not ready to be deployed yet. So just to talk about the architecture, it's very simple. So the architecture is just traditional. You have the emulator. You have we've taken the Android emulator, which is based on QEMU, which is an open source CPU emulator. We modified it just a tiny bit to add the instrumentation code that allows us to collect system call information. That's it. Well, that's it. It's a bit challenging because there are a few parts that requires a bit of challenge. But then all the information is basically transferred out, and we perform analysis there. Because not only we collect the system calls, so basically from the system call trace, we just want to provide a higher level semantic behavior information so that it's easier to deal with the data. Because otherwise, sometimes you have a sequence of open, read, write system calls. We're not really interested in all those low-level details. We do have them, but we're not really interested. We're actually interested in the fact that you are creating a file. So that is the action. Now, whether you create a file because you execute 10 write system call or 100, we're not really interested into it, although the information is there. And the communication between the emulator and the framework, the analysis framework, happens through the remote serial protocol because newer version of recent versions of QEMU come with a GDB server stub in it, so we just rely on that. That was a bet. We thought at the very beginning it was a nice design decision. It turned out to be very bad because it's slow. It's a remote serial protocol, so it's serial, so it just sends 1 byte at a time. So it was very bad. That's why we have redesigned everything. So, but just to give you an idea that the only part that we have modified is a tiny bit of the CPU emulator. Everything that runs on top of that is vanilla Android image. So we don't modify anything in the system. So there were a few points where we needed to understand how to trap system calls, and we didn't have any experience on ARM, so we have experience with x86 architectures, but basically, so now I'm just skipping a few of details here, but because they're not very interesting. So whatever we have at the very end is, it's just a sequence of system calls. So you say, good, you're doing all this effort in the emulator to have strays, right? Well, hold on a second. Well, not even yet here, because here, okay, this is the part that associate already a system call with a specific process. So all the information between square brackets are, the addresses, virtual memory address of where the PDE starts and the PID of the process and the name of the process. So, and that to do that, we need to do virtual machine introspection. But basically, whatever we have here is, yes, it's basically at this stage strays that runs within an emulator, okay? But now the juicy part is still missing, because whatever you observe here is just, the classic operating system semantic action, so creating a file and things like that. What we're interested in is again, capturing also the Android-specific behaviors. So before, of course, we collect system calls, we need to associate a system call with a thread, because otherwise you're not able to track the behavior of a thread, of a particular thread or a process. And to do this, we just do a classic virtual machine introspection. So we're relying on data structures that have been unchanged for many years. So it is very unlikely that those will change in the future, okay? So the way that we do it, sorry again for the color, but basically we just rely on the fact that, the way that Linux kernel works. So whenever you enter kernel end, so in kernel space, you have a kernel stack associated with a calling process. And the kernel stack has by default 2 pages. So 8K of memory, virtual memory in total. So at the top part of that page, there is an address, and that address points to the thread info structure. Then we read that address, we follow the structure. Within the thread info structure, there is a pointer, so another memory address that points to the task structure. We follow that address, and then we find basically all the information we need to understand for the process. So the PID, the thread group ID, the process name. It's truncated at this stage. It's okay for us. So, so this is how we do it. Of course, it's not just the mere following pointers. We need to use the right API calls, because those pointers are addresses that are valid within the guest operating system that runs on top of the emulator. So we just need to use the right QEMU API call to read those addresses. Now, the real interesting part comes here when you have inter-process communication, right? So let me just walk you through a very simple fictional application to understand, what happens when there is an inter-process communication going on. Let's assume that you want to send an SMS. 15 minutes, right? So let's assume that you want to send an SMS. You need to get a handle of the SMS manager, and then you just invoke SMS text message to send the message, basically. And here there is all embedded the magic, so all the permission checks and the fact that actually send text message is a remote procedure call. So you call it like as if we're in your address space, but it's actually something that you are invoking on the ISMS service. So if you unroll this down here, you have to locate first the ISMS service, and these already issue a binder, so in an inter-process communication on the system, so a system call, okay? I haven't shown this here to simplify the slide. But basically, you keep on going ahead, sorry, and basically, the part that is actually very interesting for us is the last line, where basically you are effectively issuing the IPC, the final IPC, where you want to send the message, okay? And whatever happens, so without looking at the details, you'll see a few keywords that are parcel. Parcel will just get back to that concept. But basically, a parcel is just a marshaled blob of data, okay? Because you have an object in your address space, and you want to send this object in another address space, okay? If you just send and the object has references to memories. If you send the object right away, it doesn't work, because, of course, the addresses don't make any sense in the other context, in the other process context. So what you have to do is just to marshal, to serialize the object. The way that you do it is just by using parcels. So by basically implementing an interface called parcelable. There are other ways, but we'll see this one for the time being. So what happens is that when you have this transaction, everything is just issued through one system call, IOCTL call. And this is another thing that we observe, because we observe all the system call, right? Unfortunately, whatever we see is this. So in IOCTL, a file descriptor, a command, and a blob of data. So, well, not very interesting, because again, it looks like strays can do this. So what we would like to see is actually this. So we would like actually to understand that, oh, this is communication with the ISMS service. You want to invoke the method send text, and that is the information, like the destination number and the blob of message that you want to send out. Now, the way that it works is that for a first part, it's quite trivial, okay? So you just need to parse a few data structures. So when you do see the IOCTL code, you just need to parse a few data structures. The first one is called binder write read data structure. That contains a few fields. One of them is actually a write buffer. It contains, that points basically to a sequence of binder commands and binder transaction. We're interested in the transaction. Binder is used also for other things, but in the system, we're interested in the transaction. So we do this parsing, and then we reach the transaction. At this point, there is another data structure. It's called binder transaction data. And basically, by parsing again this data structure, we're able to retrieve all the information, okay? Now, the tricky part, I mean, here is quite simple because all the parameter here, there are primitive types. So you have strings and integer, okay? Or basic type or primitive type. So something that you can easily deal with because there are functions that are offered by the SDK, by the system to read those information. So you can use read int, read string, to actually read out this parceled information, the information that are marshaled, okay? The problem is that sometimes, or often, you have complex objects that are sent over, okay? So you need to unmarshal this object if you want to understand what's going on. There are two options here. Either you write the code to unmarshal everything. And the problem is that there are, the last time that I checked, that there were more than 300 Android complex objects that are involved in IPC calls. And so you don't really want to write all the code. I mean, as a researcher, you want something that is a bit more scientific and also less error prone. And also because the next version of Android might just add more objects and we don't have time just to keep up with that. So we just want something that can do it, maybe work automatically. So whatever we came up with, it's actually quite simple yet effective. So we came up with the concept of an oracle. So basically, whenever we have something we don't know anything about, we just ask an oracle. So an oracle is just, in our case, it's another emulator. In this case, it's just shown in line, but all the analysis happens offline. So it's just another emulator. This time is a vanilla emulator that runs an Android image, the same Android image that you run in the other emulator. And it runs an application that just receives the blob of data. It receives also the signature of the methods that you have, that you are analyzing. And you know that because you're relying on the Android interface description language, because this is IPC invocation, so you have the signature of the method. And basically, we just ask the system to deal with the problem. So we use Java reflection. We locate a field that's called creator that knows how to unmarshal the data automatically. This is in one case. It's a bit more complicated than the way that I depicted it. So basically, there are three different ways that you can marshal and unmarshal data. Okay. So one is by using the primitive types. In that case, you just use the API, but there are a very limited number of primitive types, so it's not a problem. Then in the other case is when you have this creator field. So through Java reflection, you try to locate the creator field in the blob of data that you know what type is it because you have a signature of the method. If the creator field exists, then you invoke the creator because it knows how to unmarshal all the blob of data for you. So that is just automatically done. And there's another case. Basically where you don't really have a creator field, and you don't even send the whole blob of message in the IOCTL call. And so you send either references to memory or a file descriptor to be sent to the remote party that needs to remap the shared resource, okay? And this is done for two reasons. So one, if for interfaces where you don't really have an object, but you have a template, for instance. And in the other case is also to create, when you have intra-process communication, so you still use IOCTL call, but instead of having the IDL descriptor, because you don't have really a communication with the remote party, you use binders and you use references to the other space of the process, okay? So whatever happens is that if it is an IPC invocation, it's very simple to do it automatically because you just need to locate the creator field and you invoke that, and all the magic happens there. If this is not the case, then you have to basically fetch the information that you have in the memory address space and dump it to be analyzed later on. So this is just an example because it gets a bit complicated when you look at the complex objects. This is just an example of how it works when you have to deal with primitive types. So very, very simple. So whatever is, we receive as an input, the Oracle receive as an input the signature of the method that you need to analyze, which basically is all the types, and then the blob of data. And basically the first type is an int, and then we use the right function to the right API to read this int that is marshaled. Read int. In this case, it's just, it's marshaled very easily because it's just a little endian notation of that number is an hexadecimal. You know that an int on the architecture is 4 bytes long, so you know where the other objects or the other type starts. So 4 bytes ahead. When you have a string, it's the same thing. There are a few things that you need to know about. And everything is taken care of by the read string API. The first byte encodes how many, what is the length of your string, and then you have Unicode representation of the string in there. And you keep on doing this for all basically for all the primitive types. Again, whenever you don't have a primitive type and you have an object, then the first things you want to do to understand whether the object has been marshaled or serialized by the system to perform this IPC invocation. And the way that you do it, basically, there are a few things that you do with reflection, but the most important one is that you need to locate this creator field. And the creator field is something that the developer had created that knows how to marshal and unmarshal the application. Okay? If the creator field is missing, then it means that you need to resort to the other techniques, which is basically to look at the reference. The reference is just the memory address that is in the address space of the process to retrieve the object and to dump the object to be analyzed later on. So one other thing that we do is, and this is useful for two reasons, is just to acquire a higher level semantic of the profile that you have that you are analyzing, but also it is useful because, as I mentioned before, if you're not dealing with AIDL objects or objects that are involved in IPC invocation, and the call is not intra-process, then the other case is that you have a file descriptor that is shared. It's shared through a virtual device called dev ashmem, ASHMEM. And to do that, basically, we need to understand what is the file descriptor that refers to that shared memory. And there are a few system calls involved, because there is an open system call, and there is an open system call, there is an ISTL call, and there are a few mmap system calls. The problem is that we need to relate all those together, because we need to understand that all those are operating on the same resources, and therefore that is the file descriptor we need to use to retrieve the information from. So whatever we do is just, because it's just data flow analysis, but it's a coarse-grained one because we don't perform any taint tracking, any taint information, because our level of granularity is just system calls. So we don't know anything that happens between two system calls, okay? So the value-based data flow analysis doesn't work well in general, but it works quite well when you have file system-related system calls or network-related system calls. So whatever we do is we represent the system call as a graph, where each node is a system call, and you have just an edge between two system calls if they depend on each other, which means that there is one system call, they define a variable that is used by another system call, okay? And this way, it's possible to basically track related system call and then to replace all of them with a higher level semantic action. Like the example that I've made before, instead of having in the final report open, read, write, all those system calls, we just replace all of them with file system access and the resource that was accessed or the file that was created. The same thing happened for network communication and a few other things. Okay, so this is just an example that is cut there. Sorry, but basically the open system call define a file descriptor 0x13 that is used in other system call, the one highlighted. And by representing everything with graphs and the relation of dependency, you're able just to connect all the things together, the related one together. This one is, how much time do I have? 3 minutes. 3 minutes, whoa, very good, very good. This is very simple. So dynamic analysis has limitations that basically you execute only You observe only whatever you execute. It seems, like a very simple sentence, but it is actually true. If you don't provide the right input, you don't explore other paths. So there are challenges there. It's an open research. There are approaches to deal with this, but they are quite computationally intensive. So what we're trying to understand is actually, can we improve a little bit qualitatively, at least, the code coverage or the behavior that we discover with a very simple approach. So a lot of information are provided in the manifest. So if you remember before, an application might register itself to be a broadcast receiver for SMS, okay? Then in that case, we inject SMSs. So we try to see what happens when application registers for those events, right? And there are a few others like boot complete and things like that. So what we observe is, excuse me, what we observe is that by just doing this very, very simple stimulation technique, it's more like a fuzzy-like technique, but we're still able to discover, on average, 25% additional behaviors on more than 60% of the samples that we have analyzed. And we have analyzed 2,900 samples that are coming from different repositories. Excuse me. Just to provide a very, very simple example, if you see SMS replicator there overlapping with the OWASP logo, so if you execute the application as is, you don't observe any behavior, because the behavior of that particular malware is just to replicate SMSs. So incoming SMSs are replicated out. So if you just execute it and observe the behavior this way, you don't see anything. But if you stimulate the application with that very simple approach, you still observe 4 additional, no, it's actually 6 additional behavior. So not only SMS that are sent, but also file system accesses and network communication. So it doesn't provide any guarantee. It's just a low-hanging fruit effort. So we just wanted to do a little bit more since we are at it. But of course, this has calls for room for improvement because it's not just the end. In terms of behavior, these are the behaviors that we have observed. So some of them are traditional behavior that you can observe on a traditional system, like network access end, okay? And other are just, specific to the mobile environment, accessing personal information, contact, SMS, location, and so forth and so on. This is a very quick breakdown of things that happened on a data set provided by McAfee, I believe around 1,300 malware, Android malware. And you can see how the stimulation improved in some cases, like for accessing personal information, we observed over all the samples, 40% of samples that accessed personal information. By doing the simple stimulation, these increased to 66%, and so forth and so on. So there are a few breakdowns here, but I don't have time for a demo even, I believe. But you can go online, so you can see whatever the output looks like. So the behavior is there. And the takeaway is just basically, that's the first effort that we're doing. Still, a lot of work has been done, needs to be done. And so our goal is just to share data, so to share the data of our analysis. So we're planning probably to make the whole system available open source. Not now, because we're heavily working on it, but maybe in a year's time. But the whole analysis is there, and you can submit sample, you can receive back the behavioral output. At this time, you don't have all the details of the system called trace with all the information collected, but we will make available that as well. So the idea is actually to build on top of this, because now that you're able to reconstruct the whole behavior just by looking at system call, then you can rely on machine learning, for instance, being used quite successfully to analyze the slew number of events and understand, whether something is malicious or not. You can enforce policies because you know where things are happening. And there are a few other things that you can do, but I don't have time to talk about this, but they're here, and probably there will be slides available also. This is part also of a project. I'm hiring 2 postdocs, so if you know good people that want to do something, contact me. Very last things, thank you all. There is a conference in a few weeks at Royal Holloway. It's called DIMVA. It's a good program. I promise just to be very quick on that. So this is the conference, this is thank you, this is conference, this is thank you. So thank you all.
Thank you very much, Lorenzo.
Thanks.
Any questions?
I'll be around tomorrow as well, and at the dinner this evening. So we'll just have a few beer, 3 more, 4 or 5.
Any questions at all?
We can go online. Is it here? Oh yes, now it's all screwed up, but I just wanted to show this one. Okay, this one is I don't remember the sample. So the label that is received is Task Killer Pro, but basically what it does is that it accesses a few information. If you look here, like the device ID a few times, but then it creates. So exploit D is one of the well-known exploits that were running around a year ago or something to exploit Android systems. And so you can see the behavior. So the exploit is actually created at runtime. You have the file, you can download the file, and you can see all the steps required in the exploit. And you can see that there is a privilege escalation here when the exploit, I mean, it's a vulnerable image because it's a gingerbread image, and the exploit worked on gingerbread images. So you can see basically the whole behavior here. And again, you have this is the website. Should I say sucks a bit. So we're working on. I mean, it's on a priority list of to-do things, but it's one of the latest one because we just want to deploy the new analysis that basically is able to provide a lot more accurate information on that. But basically, you can have the whole. This is the whole behavior for 10 minutes of execution. You do see both low-level behavior, like all related system call a high-level behavior, Android-specific behaviors here. And or network access here, you don't have any network access, I believe. Oh yes, you have a few network access. This is just a random sample, of course. It might not be too interesting, but yeah, basically, everything is here. So all the information are here. Sorry, it was a quick demo because I know that it's sort of tie break.
Any other questions at all? Thank you very much, Lorenzo.
Thanks. Thank you.